technical stuff related with most related to the MEMS fabrication and MEMS devices, and also some non-regulated. And I will use some microfluidic technology to adapt the global health problem, actually, some HIV global health problem. So first, so I developed some microneedle array using X-ray lithography. This is one of the light sources. So I made this kind of sharp needle array to extract actually blood. Generally, in most of the technique is focused on the drug delivery, injected drug or high molecular protein to surface. So we call it transdermal drug delivery. But till that time, actually 2006, nobody can develop a method to extract the blood to adapt it ubiquitous glucose detector or something like that. The previous lecture tell about the usability of blood actually as an analyte for electrochemical sensors. So I developed a microneedle array first, and then I adapted a method to fabricate three-dimensional microstructure with exposing three basic expert equipment. So actually, as you've seen, you assemble three mask array, and we can make a three-dimensional, fully three-dimensional structure we can generate it. So this is the one thing I developed. It's a collocated sharp needle array. It's useful for extraction of some tissues from inside of the body or tissues. Actually, I developed this kind of tool to adapt capsule type endoscope. So if you see some tissues or cancer or cancer spot, and you can extract some tissues using this kind of needle or biopsy tools. And also like that, there is some knife shape, and then it extracted the tissues as well. And also it extracted some liquid or inject actually some drug inside of the body, actually encapsulated inside of encapsulated type endoscope. And the other application is there is some pictures like fully 3D structures like the honeycomb structure. It might be used for tissue engineering as a scaffold. And also I more developed the microneedle array fabrication, not only simply one-time fabrication. I just adapted this fabrication method, mold fabrication, using the PLLA and PLTM. It is a highly biocompatible material using a hot embossing process. And I made this kind of array of microneedle. This is the hair. This is a 36 gauge needle. So it's so smaller microneedle array too, using transdermal drug delivery. And I use this kind of needle to test the pain test, because the smaller microneedle do not irritate some of the nerve signaling distributed outside of the skin surface. So at this kind of the the 700 micrometer height of needle will not be irritate much of the neuron. Actually, it will not give any pain. So I call this is a painless microneedle array to deliver the drug, actually high molecular protein. So I also to use some of the poor mouse and then extracted some blood. Also, I did some glucose test with the commercialized test. Very time, our microneedle array can be used as a drug delivery. And also, I just changed the fabrication method from microfabricate polymer to the nickel array. So nickel can be used as some hard material for electroplating. So I made some sharp needle array. It encapsulates is an endotype, capsule type endoscope here. So I extract some tissues it successfully worked. Actually, still, this kind of the type of the part or function not developed yet, because it's hard to extract the tissue inside of the microcapsules. And also, I'm working at the robotics engineering department at medical robotics. We also try to develop this kind of functionalized endoscope to extract some cancer tissues inside of the cell and other tissues. And it also commercialized by my advisors, and also this kind of patches can be used, or you can buy throughout the company with them, and it is commercialized for a cosmetic application. So you can tap it in your skin, and then the colorate is enhanced, degreased, or you can use this kind of thing instead of the laser things to liberate the coloration of your skin. That might be one of the tools for a global health system to extracting some actually blood, or inject some drug, and for point of care testing. So this is one part of that. So the other also I presented about that aspect of part aspect of view. It's not a full system. So I dedicate the work of the Prof line. It can be fabricated some small features and then generate some nanostructures. And then I using some electro spray method, and then I tie on a nanostructure like that way, and then I immobilize some biomolecule, so pegylation onto the silicon oxide substrate, and then it can be used as a DNA array chips, as a nanoscope. It has a nanoscope, and also this part can be sprayed like something field, actually electric field, plus and minus. It confined in the virtual area, and then you can move the DNA stuff. So you can use this kind of thing as a PCR machine, it's localized PCR machine, and it's mixing the PCR DNA. So the reason why we develop this kind of chip is without any physical wall, we can freely change and mix and do the polymer chain reaction inside one single chip. Still, actually, we don't know how can use this kind of the chip, but it has the possibility to adapt it the point of care testing without any heavy PCR machines. And also, we use some microfluidic chip to mixing the cell and some liquid without any shocking of the osmotic shock. Actually, I needed some tools to mixing the cell and the sugars to freezing the cells. We call it generally as a vitrification needed without any crystallization inside of cells. At that case, we should mix in general gradually with the sugar into the cells. So without using that, and then the cell feel the shock or osmotic shock of sugars and they die. So we use this kind of microfluidic chips as mixing devices. That is one of the examples how can use the microfluidic chips to biological applications. The other thing is I made some inkjet print head without any nozzle using a piezoelectric material. It's simple actually. We vibrate on the surface like this way, and this kind of concentric circular shape make a leaking pressure, and then it matches here, and then it aggregates some pressure, and it overcomes surface tension. It generates some drumming. The most important part of this equipment is there are no need of nozzles like the orifice. Generally, the tools in the inkjet printer, they always need a nozzle to generate drumming, but it does not have any nozzle in the surface. It can be adapted for biomedical applications such as drumlet cell encapsulations. So we, as you can see here, there's some nozzle here, and then maybe generate some bubbles actually GroundNet. It encapsulates the single cells like this here, single cell, one cell. Actually, total is 1 picoyear. So we can see after 3 days, 6 days, 12 days, all different cells and shows a high viability than another conventional method. So this kind of the method can be used for tissue engineering to build up some structures with the cells. So we use this kind of the facility to build up the bladder tissues, actually. The bladder tissues as cross-checking structures. So here we printed out the cell encapsulated GroundNet like this way, like we showed the bridge or layer by layer, 1, 2, 3, 4 layer, as it showed the high viability with the layer structures, with the collagen matrices. And this kind of material, the method can be used to generate bladder tissues at this time. Also, we analysis how many cells is encapsulated in GroundNet during the printing process. So we evaluate this kind of the method, the statistical method. It follows Poisson distributions, so we can control how many cells encapsulated in the cells based on this kind of the analysis method. And also, there is a more specific application for single cell encapsulation of GroundNet. Based on the RNA extraction technique, there is one problem is noise from other side of the RNA in the air, actually. So it's hard to extract the single total RNA from single cell. During the manipulation, there's a lot of noises occur. But our platform can take care of that kind of the encapsulate from single cell from bulky cells, and then we can extract the total RNA like this way. Even single cell, in single GroundNet, we can extract the total RNA, and then we can extract a lot of significant genes from 1,000 gene library. So we use this kind of the tool to find it out, present the cells from our samples, what the candidate of that, and then we can take it out from a total RNA analysis. And also we can use some spray technology to encapsulate the cell in high throughput, and then we submerge this kind of the encapsulated cell into the liquid nitrogen, and we conserve our blood without any duration time, actually. So we get a higher viability because this kind of the small area enhances the heat transfer, and then it inhibits generation of crystallization inside of cells. So finally, I try to tell about the final application of microfluidic chip to point-of-care testing. Actually, this is an optical-based system. So optical-based system is not good for point-of-care testing because you need a microscope. So you cannot hand it out with a microscope in the field. But I try to make some microscope, handheld microscope without any lens system. So it's actually shadow imaging of the cells. If you capture some specific cell from whole blood, and then you can see the cell, how many cells in your chip, and easily can define how many sample or cells actually we target the CD3 positive and CD4 positive T lymphocyte is attacked by HIV virus. So when you know about the number of the T lymphocyte, and then you can properly treat it with a cocktail method of drug. If you don't know, you die because the development from HIV to AIDS. How many people die per day? 30,000 per day without any $1 experiment of that. So if you develop this kind of system, and you can save 3,000 people in Africa in a day. So we focus on this kind of the platform using the CCD image system with the shadow imaging. Actually, we call it the more general is the holographic images because they are shadow images. I stopped by some conference in this year, and then some of my coworkers already developed this kind of machine, 3D holographic images. And then when this kind of machine actually the cost is $1,000 most, but it can be used as a 3D confocal microscope right now. Can you imagine? So $1,000 confocal images, they made it. And there is some very expensive to capture the CD4 particle. We are using some biotin conjugated some antibody. And then also, I freeze dry these chips. Nobody can do that kind of things work because till now, antibody itself you buy throughout the form of liquefied form. Because you can do the liquefied form of the antibody. You can buy it, but nobody can do it based on the biochip size or biochip application. So we did it, this kind of the application like that way. The problem is why we cannot do this kind of the application to liquefy. We need a liquid nitrogen imager of the surface. But at that case, some heat expansion and shrinkage rate is changed of each material, and then that kind of thing is break your chips. But the therapeutic method using a double cell is a film, and then it compensates, get kind of the stress of shrinking stress, and then it successfully survive after that kind of high heat transfer stress. And also I did some functional tests, and it works well. And this is the optical principle, how you can detect of that. And this is what I use for the lensless imaging of cells, capture of cells. Simply, you use this micro CCD chips. This is, how much is it right now? $20. This is $700 for big size. But you can use this kind of a small size of CCD, $20 as a webcam. And you can use it as point of care testing of to find out or count the cell. Actually, some company they sell some cell counter is $8,000 right now. So you can make it $20 with counting the cells. So there is one example how can you counting using the microscope and the fluorescent images like that way. This is a recently published method. How can we detect each images as a different cell types and capture in microchips? There is some signal actually, the pattern matching method. There are libraries, and we can detect which kind of cell and capture the different shape or different diffraction pattern of that. So this is the ordinary counting method like that, following of the 2 chip and 6 channels, and 1, 2, 3, 4, 5, 6 different person counting manually. It takes one chip per one channel. It takes 1 day actually to counting every single cell, because the number of the cell is several thousand cells you can capture in the chip. So this method can be overcome. Automatic counting method is overcome this kind of the manual counting method. So we can count entire chips within actual minutes. So it can be adapted upon point of care testing. So there is some testing. Here's the evaluation method, and then actually you can use this kind of chips here. Flow in, actually the blood in and capture this kind of cell. There's a magnified images. Without any kind of the lens image, you can directly see of the cell shadow and then counting it directly. So this is so I go to the tangent actually with this kind of platform here. This is me actually. This is the operator at the tangent laboratory. It's not me actually. They operate by themselves, not me. So this is one black box. It contains some CCD sensors, one computer. That's all. It substitutes all the text reader, flow cytometry. Okay, so it might help the people do test it without any much cost. So the result shows a very good result of R-scale value and some first positive and negative result like that way. Here, the same chips of that is good result showing the good result can be clinical use. And the other thing is we also apply this kind of chip without any the surface chemistry. We use some filter chips like that, and then capture some specific cells with the filter devices, and then we use some tagging, fluorescent tagging, and directly counting. But still, we try to making some fluorescent-based toxicity without any range. But there are a lot of the group they publish and present about that shape of that kind of equipment for fluorescent detection without any range. So another application is to capture any ultrafield using this kind of chips. It's the early detection of sepsis, because patients should be detected with some sepsis symptom, and then you should go to the hospital. But it's an urgent reaction, and then you die without any proper treatment. So in the home, you should use this kind of chips. It means you can check it how many neutrophils activate in your blood, and then you can decide if you should go or you should treat it for some antibiotic drug. But it works well, but still needed to adapt it for clinical trial. So another application is we also can see E. coli. E. coli is the size is 1 micrometer by 3 micrometer size. But imagine you can see 1 micrometer picture size without any rarities. That is the most important impact to detect E. coli based on some disease. And also, we use this kind of the webcam can be used for a battlefield. So it means we capture some carbon monoxide here, and then we can use this kind of the chip as a cell-based sensors. And then carbon monoxide feels some toxic environment, and then the beating it changes like this way. So beating is monitored by this kind of the CCD system. So it can be easily adapted to cell-based biosensors of beating, shape, and morphology, how it can be detected the cell behaviors. Then also, I just tried to capture the single virus using a surface chemistry. This is some structure of the HIV virus and the way to introduce the cell. One of the target the protein is GP120 primer and GP41 primer too. So GP120 is one shape. It can be captured by CD4 actually. CD4, while the T lymphocyte are taken by virus, this is the CD4 capturing site of GP120 the protein, and then it unzip, and then GP41 activates some probe, and then fusing inside of cells. Unzip is the virus actually morphology change. But it's not fully decided yet about that mechanism, but we are targeted for 2 different proteins like that way. And then we use the anti-GP120 as a target cell, target protein to capture some antibody, to capture the virus antibody like that way. And then we use the quantum dot. So this is the size of the virus is 120 nanometer. So we cannot see the optical microscope, but it amplified by this quantum dot. Actually, this is source of light. So it diffuses out. We don't care. It diffuses out. We don't worry about the shape of the virus. We just want to know whether it is or not. There is or not. So we can quantify how many virus in your blood or your samples. So here you can see about spot, a dual color spot. Actually, you can. So we try to use the beta, the virus or the dust. So we use a yellow color. So the important thing is here, 10 microscope, you can use 100 of the specific things. Yeah, this is the same use for body capture. Thank you.
We have time for some simple questions.